All right, welcome back again, guys, to the channel. If you got this far, it means that you may or may not have been watching the series of the playlist with the trigonometric identities. Now, in this video, what we're going to be doing is looking at the half angle identity. And we're going to start with the unit circle just to get the idea going. Now, we're drawing the y and the x-axis just the same. And we're just using the top half of the circle because we don't need the entire circle. So we're using only the top half like that. Nicely done. Right? And inside, we're going to construct the triangle where the hypotenuse is 1, because that's the radius of the unit circle. And we're going to have that 90-degree triangle here. And again, this angle right here is theta. The length of this side is 1 unit, right? And if you're going in the x direction, it's going to be the sine of, not sine, the cosine in the x direction. So it's a cosine of theta. And in the y direction, it will be the sine of theta, right? Now, what we're going to do also is to incorporate a circle theorem identity. I don't know if they call it an identity or a proof, right? I don't really know the name of it, but the concept is that if we have two angles that are subtended from the same arc length, right, it means that the angle at the center is twice the angles at the circumference. Meaning, if we have a circle like this, rather a dull circle, right? But let's make that circle like that. And we have an arc length, like an arc length of this piece right here. And in this, from this arc length, we have an angle going all the way up, touching on the circumference and coming back down. And we also have another angle going to the middle and coming back down, right? So it says that here, this angle here is twice the angle at the point right here. So if this is x, this is 2x. That's basically what we're saying. And if this is x divided by 2, right? So it's this same idea that we're going to be using right here to get to the half angle identity. So we're going to use this upper half of the unit circle. So it means that we're going to have this arc length out here being the same arc length that the two angles are subtended from. So if we make the x-axis one of those lengths, so we need it to be touching the circumference of the unit circle on this side. So it means that we're going to have this triangle looking shape right here coming all the way over here. So this side is subtended from the same arc. And if we, from this point all the way down here, you can see where this angle here is at the center here. Well, yeah, at the center, the origin. And this angle here is at the circumference. Now, they're subtended from the same arc, which means that this property here holds. So it means that if this angle here is theta, this angle right here is theta divided by 2. Let me go over that again. So because of this property here, we have this arc right here, which this angle is subtended from, and this angle here is also subtended from this arc. It means that this angle here is twice the angle at the circumference right here. So if this is theta divided by 2. So we're going to put that piece in. Theta, let's draw an arrow out here just to indicate that. That's theta divided by 2, because I can't write that in that space. Now pay attention closely. This is the origin of the unit circle, and this is the circumference. So it means that this distance here from this point to this point is 1 also. So if you pay attention to this triangle, what we have right here is an isosceles triangle. And you know that the properties of the isosceles triangle is that these two angles right here are equal. So if this is pi over 2, this angle right here also, let's bring an arrow out, is pi theta, over 2 also. So these two angles are equal. Now, we can say that if we get a nice little vertical line that's perpendicular to this side, right? And why we're going to get that is because we need to know what the distance of this line is in terms of sine or cosine, right? So we're going to get a nice little vertical line, right? It's perpendicular, not vertical, but it's perpendicular to the base of the isosceles triangle right here. So it's coming from the vertex point right here. Now, it means that this right here is a 90-degree angle, as well as this over this side is a 90-degree angle. So you can see that we have two right triangles when we use a perpendicular line to get that isosceles triangle in 2 equal half, right? Nice. Now what we can do is to get to the distance of this line in terms of sine or cosine. Let's see what happens. Now this angle right here is theta over 2. So, and this here is the hypotenuse. This purple side is the hypotenuse. So if we, I think we can take this away because we have already garnered the information from that. If we need to find the distance of this piece right here, it would be from this point here to this point here. So we're looking at this right triangle where the hypotenuse is 1 and it's this, the length of this side is what we are interested in. The angle here is theta over 2. So this would be the adjacent side. So it means that the cosine of theta over 2 is equal to the adjacent side. We don't know what that is. Let's name that t. It's equal to t over the hypotenuse, which is 1. Now again, t divided by 1 is the same as t, so we could leave that out. So t is equal to the cosine of theta over 2. Let me fix this 2 right here. Now, if this side is equal to the cosine of theta over 2, let's put that in. And it means that it is half of the length of this long side of the isosceles triangle. It means that this side here, so it's also a cosine of theta over 2, and we don't have to go any further. So it means the total length from this point up here to this point on the circumference is 2 cosine over 2. So let's put that piece in. We're going to have 2 cosine theta over 2. That's the length of that side. The length of this side from this point to this point, notice it's 1 plus the cosine of theta. So we can put a plus sign in between that because it's from this point to this point. It's 1 plus the cosine of theta. And we already have the dimension of that side also. Now, we're going to need to complete this triangle over here in this section right here, this triangle. Like that. Nicely done. Because we are going to be using that triangle to find the other half angle identity, right? So we're going to use this big triangle right here and this small triangle right here. Now, if you look at this small triangle right here, we know that this is 90 degrees, right? And if we need to get the length of this red side over here, we can look at the bigger picture, the big triangle. That's from this point to this point, all the way to this point. So I've labeled those in red. So if you look at that point, that is actually a triangle in half of a circle, right? Now, we know that if that's true, that's a right triangle right here. This angle right here is 90 degrees. And because that angle is 90 degrees, it makes this a right triangle. And if that's a right triangle, It means that we could use this angle right here to get to the length of that side in terms of sine or cosine. So in relation to this angle right here, this would be its opposite side, this red side. So it means that the sine of this angle, which is theta over 2, let's get that in. That's the sine of this angle right here, which is theta over 2, is equal to the opposite side. We don't know what that is, so let's use a variable to represent that, b. It's equal to b over the hypotenuse. What's the hypotenuse? The hypotenuse here is this long side. Are we seeing that? That's 1 plus the cosine of theta plus this small side. But we don't know what this small side is. So in relation to the unit circle, we can use this length here as equal to 2, because we know that from this point to this point is 1, which is half of the diameter, it's the radius, and from this point to this point is 2. So it means that we know that the sine of this angle is equal to the opposite side over this length, which is 2. So in reality, b is just equal to 2 sine of theta over 2. So in this space right here, we're going to let b equal 2 sine of theta over 2. And that's the dimension of that. And the dimension of this piece would be the fact that this, from this point to this point, is 1 unit. So this point here would be 1 minus the cosine of theta, because here is the cosine of theta, right? And we have all the dimensions we need to show you why the half angle identities are true. And to do that, we're just going to use a Pythagoras theorem that states a squared plus b squared is equal to c squared, right? And we're going to use two triangles to do that. We're going to use this small one right here. I'm going to label that in red. I'm just going to trace that over in red so you see which triangle we're focusing on. That triangle right here, we're going to use the Pythagoras theorem. And it doesn't matter which side of here is A or B, we just know that that side is C. So let's put the sine squared, sine theta all squared, sine theta all squared, plus 1 minus the cosine of theta all squared is equal to the 2 sine theta over 2 all squared. That's what we know based on this red triangle in that space. Now, we know that we could rewrite this as just the sine squared of theta. And then we need to FOIL right here. So we're going to have 1 squared, which is just 1, minus the 2 cosine of theta plus cosine squared of theta, right? Which is equal to, if we distribute the exponent here to 2 and sine theta over 2, we're going to have 4 sine theta over 2. That's what we're going to have, right? Because 2 squared is 4, and sine squared theta over 2, it's a square right here, yeah. And sine squared theta over 2, right? Now, what we're going to do is to simplify. Let's simplify this right here. If we bring this here with this, we know that the sine squared theta plus the cosine squared theta, that's equal to 1, right? So let's bring that out front. Sine squared theta plus cosine squared theta plus the 1 minus 2 cosine theta equal 4 sine squared theta over 2. All of this right here just simplifies to 1. So we're going to have 1 plus 1 minus 2 cosine theta equal 4 sine squared theta over 2. 1 plus 1 is 2. So what we have is 2 minus 2 cosine theta equal 4 sine squared theta over 2. Right? That's what we have, and we're going to bring that bring that up top so we can see that a little bit clearer. We're going to bring that right here, right? Now, what we're going to do is we're going to divide through by 2 first, or we could just divide all through by 4 and then factor out a 2 in the numerator so you guys can see what's happening. But to keep it simple, I'm going to divide the entire thing by 2. So doing that, 2 divided by 2 gives me 1 minus 2 divided by 2 cosine of theta just gives me cosine of theta is equal to 4 sine squared theta over 2 divided by 2 is going to give me 2 sine squared theta over 2. Right? And again, we need to get to the sine of theta over 2. So what we need to do here is to get rid of the 2 and the exponent right here. So we're going to divide both sides by 2. So if we divide both sides by 2, we're going to have 1 minus the cosine of theta over 2 is equal to sine theta over 2. And I'm going to write it as all squared so that you can see what's happening right here. Now, if we take the square root of both sides, so we take the square root of both sides, what happens? The square cancels with the square root. We're left with the sine of theta over 2 is equal to the square root of 1 minus cosine of theta all over 2. And that, my friends, is the half angle identity in its true form. Right? The sine of theta over 2 is equal to the square root of 1 minus the cosine of theta divided by 2. Right? And that's just by using this small red triangle here to show you that. What we're going to do is we're going to use this other piece of the triangle, or this point, and this point here. We're going to look at this triangle over here. Let me highlight all of that in black so we can look at that only. So from this piece to this piece to this piece up here. Right? So we're going to apply the Pythagoras' theorem to that triangle in black. Notice that, remember, this side is 2 cosine theta over 2. This side is 1 plus cosine of theta. And this side is sine of theta. All right? So we're going to remove these pieces right here. And we're going to apply the Pythagoras' theorem to that triangle, which is, this is the hypotenuse, this is the other two sides. It doesn't matter which one is A or B. So we could take the sine again, the sine squared of theta, skipping a step there, I'm just squaring thing. Now, I'm adding that to 1 plus cosine theta all squared is equal to the square of this. It's 2 cosine theta over 2 all squared. And you can see where it's going, because now we have cosine over here instead of sine. It's the same process to get to the cosine of theta over 2, right? So you could just look at the previous step to see how we got to this one, but I'm just going to solve this one all the way through just the same. So the sine squared theta plus 1 minus plus 2 cosine of theta plus cosine of squared of theta is equal to 4 cosine squared of theta over 2. Right? Just moving quickly. The sine squared, cosine squared theta plus sine squared theta plus cosine squared theta is 1. So in reality, what we're going to have down here is 1 plus 1 plus 2 cosine theta is equal to 4 cosine squared theta over 2. So we're going to have 2 plus 2 cosine theta is equal to 4 cosine squared theta over 2. And we're back to this step where we're going to perform. We're going to divide through by 2 and then 2 again on both sides. So let's do that. If we divide through by 2, let's move these pieces up here. So if you bring this piece all the way up here, and we're dividing all the way through by 2, so we're going to have 1 plus the cosine of theta is equal to 2 cosine squared theta over 2. Divide both sides by 2 again. We're going to have 1 plus the cosine of theta all over 2 is equal to the cosine squared of theta over 2. And again, we take the square root of both sides. We get that the square root of 1 plus cosine theta over 2 is equal to cosine theta over 2. And that's the half angle identity for cosine theta over 2. All right? And you could get to tan theta over 2 by using the principle that the tangent of theta over 2 will equal to the sine of theta over 2 over the cosine of theta over 2. So I will leave that up to you to prove that that is true, because we have already got the foundation of those identities, right? So what we're going to do is look at the double angle identities, and we could have showed you how this was derived from those double angle identities, because they have some nice properties as well, right? So we're going to close this nice little series or session out with the double angles identities, and we'll be finished with trigonometric identities proof. All right, let's go. So in the previous videos in the series, we would have proved that the sine of theta plus alpha is equal to the sine of theta cosine of alpha plus sine of alpha cosine of theta. And would have shown that also the cosine of theta plus alpha is equal to cosine of theta cosine of alpha minus the sine of theta sine of alpha, right? And if you want to incorporate the difference of the angles again, it's just a sign change right here when you're taking the difference. So we're not going to focus much on that. What we're going to focusing on if we're adding the same angles, right? So it's a sine of 2 theta. We call these the double angle identities now. This also can be rewritten as the sine of theta plus theta, right? So in reality, what we have over here on this side is the sine of theta, the cosine of theta, plus the sine of theta cosine of theta, which simplifies to 2 sine theta cosine of theta. That's all it simplifies to, right? So that's a sum of the identities, right? Now, if we have the cosine of 2 theta, we can also rewrite it as, let's rewrite that, as cosine theta plus theta, which is equal to the cosine of theta cosine of theta minus sine of theta sine of theta, which in reality what we have is a cosine squared theta minus a sine squared of theta. That's what we have, because we're multiplying. And then from this, we could manipulate this, because we know that the cosine squared of theta is equal to 1 minus the sine squared of theta. So this is also equal to 1 minus the sine squared of theta minus sine squared of theta, which simplifies to, and put the simplification on that side, 1 minus 2 sine squared theta, right? That's what we know. And that's the cosine of 2 theta. But we also know that the sine squared of theta is equal to 1 minus the cosine squared of theta. So we could write it as cosine squared of theta minus 1 plus sine squared of theta, right? So what I did there was to distribute the negative sign right here, because it would be equal to 1 minus the sine squared of theta. Well, 1 minus the cosine squared of theta. So it's 1 plus the cosine squared of theta, right? And then the cosine squared of theta plus the cosine squared of theta, that's 2 times the cosine squared of theta, right? Or 2 cosine squared theta. So we're going to have negative 1 plus 2 cosine squared of theta. That's what we have. But then you could use a commutative property just to move that around, and you would get to 2 cosine squared of theta minus 1. You'd get to 2 cosine squared of theta minus 1. All right? So those are where the 2 variation comes from. And these are equal to the cosine of 2 theta. Let's just switch this back now to cosine of 2 theta and sine of 2 theta. So what you will see is these 2 forms. You will see this form right here. I'm going to box that in. And this form right here. I'm going to box that in also. Right? And this form right here. Right? So those are the 3 ways in which you could write the cosine of 2 theta, right? And the sine of 2 theta is equal to 2 sine theta cosine theta, right? Now, you can use these in many ways, right? And we could have used this identity right here to prove the half angle identities, right? So there's other ways to do a lot of things in maths. I'm gonna leave it up to you to get to the tan of 2 theta, because you know that the tangent of 2 theta would be equal to the sine of 2 theta over the cosine of 2 theta, and you could prove that. So these are not formulas or identities that you need to memorize, right? You just need to know the basic ones and then use the basic ones to prove the other ones, right? Don't have to memorize. All right, guys, thank you for watching. Hope you really enjoyed this series. I really going to be doing more projects for you guys. Please to like, subscribe, share with a friend, tell a friend to subscribe, all right? So we can build the channel. All right.